Okay? But we do need to sort of think about fluids a little bit more. We kind of finished it last time. And remember, we had our three equations. Remember, oh God, I can't remember them. Pressure static is the pressure at the top plus rho GH. And then there's continuity A1, V1. If it's flowing at some area, some velocity V equals A2, V2. All right, that was continuity. And then there's Bernoulli. At any point, the expression, let me see if I can do it, the pressure at the top, the pressure at that point, plus rho GH plus 1/2 rho V squared is constant. Okay. Where this clearly looks like energy. This is kind of the energy you get from moving the volume of element or the mass of the fluid around. This is the speed, and this is the work you can do due to pressure. And when we applied those ideas to fluids, we got this expression that's constant anywhere in a fluid that's flowing if it's incompressible and there's no viscosity and it flows without friction and yada, 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 if those are all true. Okay, so this is the three, and I feel like we did a bunch of examples of that last Thursday when we talked about pressure gauges, but we haven't really done an example with this, right? We haven't showed you how to use Bernoulli. So that's what we're going to do. We're going to do a couple of Bernoulli examples before we get on to the next topic. Everyone agrees? Okay, good. Because y'all wanted to say no. I don't know what I would have done. Much better. Okay. So Bernoulli example, if we wanted to do one, I call this draining the tank. This is a very common kind of problem you'll see in books. What I don't like about draining the tank is that it's got sort of an approximation in it, but I'm going to show you exactly where the approximation is. Okay, we're going to do it without the approximation, and we're going to see, okay, this is why they do that. But it's such a common thing that comes up, I think it's worth talking about. Okay, so we have a tank, right? It has radius big R. Okay, it has a hole in the bottom. There's a hole in the bucket, dear Liza. Does anybody know that song? There's a hole in the bucket? Okay, good. Okay, I don't have to sing it then, thank God. Okay. Tank, hole in the bucket, dear Liza, and the water flies out like that. All right. So the tank, the big tank here has a big radius R. Again, I should not start singing songs and phrases from my youth, probably. And no more candy stripers. Hole radius R. Right. Radius R. And the liquid is, the hole is H below the liquid. H below liquid surface. All right, so this is H here. There we go. And Y above the bottom. Okay, so radius R, hole radius R, H below the liquid surface, Y above the bottom of the tank. All right, so this would be Y. There we go. A hole is sitting Y above the tank. And what was the question? Let's see. And the tank is at P. The tank is held at P. So the pressure up here, we're saying, the pressure here is P. So it might be open to the air, it might be closed and sealed, and the pressure is set at some value, whatever. The reason this is a popular kind of problem is this could be a fire extinguisher. We have high pressure here. This could be an open tank where you're just asking how long will it take all the water to leak out. We're going to do this as an IV bag for a transfusion. Okay, you get the idea, not as a demo. Okay, so then we're trying to solve for, I forgot what we're trying to solve for. Yeah, how fast does the water come out? How fast does the water come out? In terms of all these given parameters here. Rho, H, yada, 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 yada. Okay, here we go. So we're going to apply Bernoulli. And the key to applying Bernoulli is pick 2 points. So in an energy problem, you have like the initial and the final. In Bernoulli, you pick 2 points in the flow, and you say that thing must be equal at those 2 points. All right, so the way I'm doing this in my notes is I have, this is point 1, right at the top of the meniscus, and where it's flowing out is point 2. Okay, so we're going to equate Bernoulli at points 1 and 2. All right, see if I can not screw this up here. Let's see. Okay, so what is the pressure at point 1? All right, so we're going to say 1 equals 2. Here we go. I'm going to write nice and big. The pressure at point 1 is P. Whatever we wanted the pressure to be up there. Different kinds of problems. If it's open, it's atmosphere. Who knows what it could be, but it's some pressure, right? Plus the density of the water, you know that, rho. Gravity, you know that. And then the height of that point, and you can see it's at h plus y. Now you can kind of maybe tell that this term is kind of like a potential energy term, isn't it? Right? So it kind of, you would think, maybe it doesn't matter where 0 is. And you're right, it doesn't. Right? But let's just put h plus y anyway. Let's pretend we're very normal people who say that y is 0 here. Okay, P plus rho g height plus 1/2 rho, and now what's the velocity there? I don't know. Call it V1. V1 squared. There's an unknown. All right, our first unknown. We're looking for V2, but apparently we don't know V1. Okay, so let's say that now equals 2. Okay, what's happening at 2? Okay, this is a little weird. The pressure at 2 is atmospheric pressure, because we're talking about outside the hole. Okay? P, I'd say that's the only really ambiguous thing about solving this problem, is to know that you put atmosphere there. And then it's sort of a rule you just have to follow, or let me try to physically explain it to you, okay, real quick. I'm saying it's atmosphere because really what happens is most of this water isn't moving, and there's some streamline, right? There's some streamline that's going out of here or something. But really the velocity of this big thing is very small compared to this thing. So you sort of imagine that it's not really moving here. Because if you did sort of a static pressure calculation, you wouldn't have atmospheric pressure here. It would be higher than that, right? If I just said, what's the pressure here? You'd say, oh, it's P whatever here, atmosphere, plus rho GH, or whatever it is. But no, so that's why we're not saying the pressure here, we're saying the pressure out here. Out here, it's atmospheric pressure. And you might say, well, but there's a little flow of water. Maybe that creates more pressure. And the answer is no. We're doing this ideal thing where the pressure's high here and the pressure's low here. And that's why the water flows. Yes, if you micro zoom in into the little tube that is the hole in the wall, there would be like pressure gradient across that little hole. Right? But we're just treating this as a thin hole. The pressure in here is some value. The pressure out here is some value. Okay? So hopefully that helps a little bit. But if you're ever doing this problem, just know that the water is flowing out, and you're asked how fast it's flowing out. Even though there's water flowing out, even though it's moving, it's still under atmospheric pressure. Okay? That's the only ambiguous or tricky thing, I would say. Okay, now we need the rho GH term. All right, so rho, density of the water, G, you know that. How high is the hole above what we're calling 0? Y, the thing we called Y. Somebody asked, is this a closed container? I'm saying it could be either way. I'm just saying there's a pressure up there. Don't worry about it. Right now I said P. I didn't say it's at atmospheric pressure, so it must be closed. Okay? But we'll open it in a minute. So I'm going to put a Y here. Okay? Because this is sitting at Y. And then plus, let's speed it up here, rho V2 squared, another unknown. Oh, that's actually the one we're looking for. We're looking for V2, aren't we? Yes. Okay, so now we get to start simplifying, okay? And I've told many people about this intro physics, as everybody thinks you have to have had calculus, and the answer is no, you don't have to have had calculus, you just have to be really good at algebra, right? So people that have had calculus tend to do better. It's not because of calculus, it's because they're fast at algebra. Like, you know what I mean when I say, oh, right? You know what I'm saying? Okay? If you can do that immediately, you'll go through this problem fast. If you got to think about that for a while, that's okay, but it'll slow you down. You see what I mean? This distributes to both of these. This is rho gy plus rho gh. Therefore, we have a rho gy added to both sides. So I cancel the rho gy there, and I just cancel the y there. So I know you get that. I'm just saying this is the thing that slows people down. So we simplified, we got rid of, we realized it doesn't matter why, right? We could have called the hole 0. It doesn't matter. All that matters is the difference in height between the hole and the surface on the top, right? What else do we know? So now our problem is we have one equation and two unknowns, right? So we need another equation. There's only 3, right? There's only 3 equations here. And we need one with V1 and V2 in it, right? It's clearly the second one, continuity. So we apply continuity equation. We say, okay, well, the area at the top, so A1 V1 equals A2 V2. And we know what the A's are. They're pi r squared. So at the top is the big R. Pi big R squared V1 equals, and the bottom is the little r, pi little r squared V2. Okay? So now, how good are you at algebra again? I'm solving for V2, so I should probably plug in for V1 and get it in terms of V2. Right? That would be more efficient than solving this whole thing for V1 and plugging it back in here. Right? That would be bad algebraic hygiene. Yes? Oh yeah, so the hole has a little teeny radius here. So here we care about the radius of the hole, and there, so we're right on the outside of the hole. Yeah, we're really technically, mathematically thinking about the outer surface of the hole of the container. And it has a radius little r. Okay, anyway, so then we just solve this for V1, and you see that V1, the pi's cancel, it's little r squared over big R squared V2, right? So you say, okay, and then you get rid of this, and then you blank that out, that. All right, let's keep going. Let's bring this home here. Solving a problem. I love solving problems. Okay, so what are we left with then? We've got the P is still there. That's a known. We're fine with P. We've got rho GH. It's all known. We're fine with that. We got 1/2 rho, and then we got to plug in, V1 squared, but that's R squared over R squared, V2 squared, or V2, rho little r over big R to the 4th, oh my God, V2 squared. All right, so the V has the R squared because it's area, but then we're going to square the V, so it's actually to the 4th power. Interesting. I haven't seen anything to the 4th power since I made these notes 30 minutes ago. Equals, now let's do the other side. Atmospheric pressure, where the hole is, we got rid of its rho GH plus 1/2 rho V2 squared. Right? And there's our V2 squareds right there. So here's our unknowns now. V2 and V2, because we're really good at algebra. Yes. Okay, now we've got to get really good at algebra. Okay. So now we're going to multiply by 2 and rearrange. Again, you got to be good at algebra and know, oh, I can multiply the whole equation by 2. That'll get rid of the halves. It'll bring in 2's, but I'd rather have 2's than halves. That's just the kind of guy I am. So if I do that, I say, let's see. Oh, I'm probably just going to copy it off of here. Let's see. 2's and rearrange. Okay, so what we're going to do is everything by 2, and we're going to bring this over here to get the V2's on the left. So we're going to be left with rho V2 squared. And what would that have to be multiplied by 1 over there, and then bring this over minus r over r to the 4th. Yeah. R over r to the 4th, right? So that's all the rho v squared right there. Brought that over there, multiplied through by 2, and then everything left is going to have the 2 on it. So that went over there, so this is over here. So it's 2 times whatever that pressure is minus the atmospheric pressure. And then this little pathetic thing sitting here, plus 2 rho GH. Plus 2 rho GH. Interesting. Any other algebraic conveniences here? Oh, no, there are none. Sorry. I thought there was one. Okay. Now let's just solve for V. Okay, so I'm going to bring the rho under there, bring that big nasty mess under there, and write an equation for V. Here we go. Hold on to your hats here. A big square root, that's never a good sign, over 1 minus r over r to the fourth. Right, that's in the bottom. And then we have 2 times p minus p ATM over rho. Right, la 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 over rho. And then we have plus 2gh. All right, there it is. The leaking container problem. I'll dub in the applause. Okay. Let's see, the leaking container problem. Now, if you see this in a book, it won't be this complicated. Okay? So let's look at how you would probably actually use this problem, or actually use this solution with the approximations. Okay. So when you're looking for approximations in a physics problem, anytime you see 1 minus something, that's like a raving red flag. Make an approximation here. Anytime there's like 1 minus a ratio to some high power, screaming, make an approximation. Because when you look at this, if it's a big tank, you would imagine this radius is probably like meters. And you'd imagine the hole is like a millimeter. Okay? So 1 is if the hole is small compared to the tank. What do you have? You have r is less than r. If r is less than r, then r to the fourth is a whole heck of a lot less than big R to the fourth. And in that case, 1 minus r to the fourth over big R to the fourth is basically still equal to 1. Right? So it's 1 minus some teeny number. If it was 1 millimeter and 1 meter, that's 10 to the minus 3 to the 4 is 10 to the minus 12. Right? So instead of 1, it's 0.99999999999. Close enough. We only want 2 significant digits. So that means this thing is basically 1. So now it simplifies to V2 is just the top square root. That's not so bad. 2 times P minus atmospheric pressure, because that's the top's pressure, whatever it is, atmospheric pressure down here, over the density of the water, plus 2gh. So you'll see books solve it that way. Okay, or give that expression. But they won't show it to you mathematically. They'll just say, well, it's a big tank. The top isn't moving that much. Call V1 0. That'll be how they do it. So I'm just trying to show you mathematically where it comes from. You can use continuity to get V1 and later realize, oh, V1 is really slow. Right? The quicker way would have been to just not have this here. Right? We could have just said, oh, V1 is slow. Because the tank, the water in the tank is barely moving down as this little millimeter hole leaks out. Okay. Okay, so now we're going to demo it. We're going to do an IV problem, but let's do one more approximation. Right? So here I said, oh, maybe it's closed, maybe it's pressurized, maybe it's a fire extinguisher, whatever it is. But let's say another approximation. What if it was open? Then P equals P ATM. Right? Because the outside's at atmospheric pressure and the inside's at atmospheric pressure. Right? So what's the expression going to do then? This is 0. Right? Be good at algebra. And V2 is the square root of 2gh. Does that sound familiar? Like something you might have seen when you're studying for the exam, right? So if you drop something from a height of h and ask how fast is it going when it gets to the bottom, it's going to the square root of 2gh, right? mgh equals 1f squared. Solve for v. The m's cancel. The 2 goes the other side. Take the square root. 2gh. So that's a little expression you see all the time. And the reason it shows up now is because we've turned this into basically just a drop the water problem, right? Is we've said the pressures don't have any difference. The kinetic energy at the top is nothing. We basically just drop the water a distance h and ask how fast is it going. Right? So that's why it simplified that far, as we kept simplifying the problem to basically just dropping water. This is just drop water. Now your problem, a real problem, might have much more subtleties going on. The top might be pressurized. Maybe the hole is big compared to the container. But if you get these simple enough, it just looks like conservation of energy. Because it is conservation of energy, right? That's how we got this, right? That's the reason. Pressure was the work. Rho GH is a potential, yada, yada. I can show you that this is true. So here is a water bottle. It looks fine, right? There's nothing coming out of the water bottle. Oh, but I put a hole in it. Here it is. Ooh, there it goes. I was hoping you could hear it. Let's see. To take 126 now. Okay. So it's coming out. Why is it coming out? Because this is what we just did. This area is big compared to the hole, so if you wanted to calculate how fast the water is coming out, it actually would just be square root of 2gh, because it's open. Now what if I close it? Don't do it. Oh, I'm going to do it. Here we go. We're going to close it like this. What's it going to do? Think about what you think it's going to do. Oh, it goes really big. It stopped. Completely stopped. Why did it stop? Nothing's coming out. Why is velocity 0? Let me take the thing off. Oh, there it goes again. Now it's square root of 2gh. How did it go to 0 just because I put the lid on it? And nothing. How did it go to 0? Let's see. Why did taking the lid off have to do with it? That's what we're doing right now. I'm glad you're wondering. Why did it go to 0? How could this expression possibly give you 0? Anybody want to guess how you could get 0? Well, one thing, you could set it equal to 0 and solve for something, right? So what's happening, and I'm sure you've thought of it, you just don't want to say it out loud. What's happening is when I put the lid on, this is going below atmospheric pressure. Ah, yeah. So we must be creating a vacuum, well, not a vacuum. We must be lowering, like when I have it open, these are equal. 0, you get some flow. But when I have the lid on, it's pulling the air down, it's expanding the air. We don't want to talk about gases, but it's basically expanding the gas and reducing the pressure below PATM. So this is negative. You can't have negatives under a square root. Oh my God. Yes, you can if you add it to a positive. Okay? So this term is negative, plus a positive term gets down to 0. And then the flow goes to 0. Okay? It's okay. We had a negative under square root. It was part of a sum. Okay? It can't go further down because then you would have a negative under the square root. So if it kept flowing, when this pressure went down, we'd have a negative under the square root, and the whole thing would be imaginary. Whoa, right? That would be weird. Let's make sure that doesn't happen. Okay, if it doesn't stop, the whole world's going to go imaginary. Oh, we had a good run. Oh, it stopped. Okay, you don't have to have a lid. There we go. I'll put my hand on. Now, why does it go big when I put my hand on it? Because I'm pushing on it. But if I hold it long enough, your academic trajectory again. And down to... I love you so much. I'm just kidding. Oh, I pushed too hard. So now I'm like holding a vacuum, and it actually sticks to my hand. Watch this. Whoa. No, okay. That's my hand. Okay. All right. Okay. So this behaves completely, every approximation. It behaves exactly. If we could calculate the velocity, it would just be the square root of 2gh, because this area is bigger than that area. So I encourage you to put a hole in your water bottle and do this. Now you think I can put a hole in the water bottle and walk around with it. So I walked around like this, carrying it around, and I got here and I was like, oh my God. Because if you squeeze it, the water comes out like that. So I got here, I looked pretty, I looked like I need what's in the next example, which is about catheters. Okay, so let's do the catheter problem. So this is this basic problem. So now we're going to apply it to the real world. What you might do in your life is a medical example. Okay. Let's see. Oh no, the opposite of that is why you need a catheter. You can't urinate. I had that medical point backwards. I apologize for that. Okay, so now we're going to do real world numbers here, and we're going to learn something. Maybe. I mean, let's not get too ambitious here. Okay, so we're going to do an IV transfusion here. All right. So you can see how some of these just letters here turn into real things. IV transfusion. And I have some pictures to help illustrate the point. They're all completely important and critical to the lecture. Here we go. Okay, so say you're a candy striper, which I did check was an okay thing to say. So you're a candy striper. And you've got a 1 liter IV bag here like this. right? 1 liter of whatever they're going to put in, blood, say. Rho is 1020 kilograms per meter cubed is the density of the solution. I guarantee if the density is marked on the bag, it is not in kilograms per meter cubed. So you'd have to convert that, okay? And the mean orderly says to transfuse in 8 hours, right? They want this 1 liter to go in 8 hours. And the question is how high to place the bag. So this is why all candy stripers must have a degree in physics if they're going to be able to do this. And you know you have to place it high, right? So anytime you see somebody with one of these bags, it's like way above their head. Right? Why is it above their head? Is it to keep little kids from coming in and putting stuff in the bag? No. Because they're using gravity to shove it into your arm. So you think physics doesn't matter. Every patient in the hospital is using gravitational potential energy to infuse. You would think, wouldn't they use a pump? No. We're not spending money on health care. We're using gravity. It's just a rod in a bag. I mean, give me a break, right? So let's see. So then what happens is, it's always the case that the person's down here. None of this is, to scale. And it's going into their arm. And if we zoom in on the arm, you'd have to take a few things into consideration in this calculation. Is the thing going into the arm is called a catheter, okay? If you watch a lot of CNN, like I do recently, you would think that catheters are only put into your private parts, right? That's what all the commercials are about catheters. But any flexible thing that goes in your body is a catheter, okay? So when you get an IV, that thing is also a catheter. It's not just things to let you fly your airplane longer, okay? So the catheter has a radius, sort of the small radius, of 0.3 millimeters. You want it to be small, right? Because it's inside the needle. It has to be small enough to go in the needle, and the needle goes in your arm, and somehow they remove the needle, and the little tubing stays in your vein. And then here's something else, is the pressure in your vein is not atmospheric pressure. It's higher than that. Remember, so when you're checking your blood pressure, it's 120/80, but this is a vein coming back, so it's a little lower. So let's say that the pressure here is 50 milligrams of mercury, because that's what they're going to say, millimeters of mercury here. So you're going to flow into a region where it's 50 millimeters of mercury. And you got a bag and yada, yada, yada. Okay? So the question is, could you do this? Right? Could you set up this situation? Let's see. I found this example. I'm not sure what's going on here. I think this is Halloween related. This will be on the exam. It's 2 sources, and it's going into someone's mouth, and yeah. But here, let's get back to a real example. See here, it's way up in the air. How high does this disorderly have to adjust it here to get it in there? Orderly. There's an 80s movie called The Disorderlies, which I highly recommend. It's the Fat Boys rap group. Highly recommend. So what you got to do is, most of the numbers you need here were sort of given to you, pressures, radii, but you got to deal with this medical part. We want to transfuse 1 liter in 8 hours. What does that mean? Okay, so we didn't talk too much. We talked a little bit about flow rates. Oh my God, Q equals what? The flow rate is clearly, it's 1 liter in 8 hours, right? So that's 10 to the minus 3 meters cubed in 8 times 3,600 seconds, right? So now you have a flow rate of 3.5 times 10 to the minus 8 meters cubed per second. So you converted it to MKS. So you tell the doctor, hey, I converted this to MKS. And they're like, okay, if we could pay you less, we would. And then you got to know what to do with the flow rate. I think I briefly said this last time, but anywhere you are in a flow, the flow rate is basically what's happening here with AV and AV. Right? You have to conserve the flow rate because you have to conserve the amount of liquid. So it's really just AV. So V2A. Or now let's see, did we call the high one 1 last time? Which one was 1? Yeah, okay, let's call it V1A. Screw up my notes. There we go. So we're going to call the bag area V1, up in the bag. Right, and then you say it's equal to V1 times pi. Oh no, I'm sorry, we're doing this down at the bottom too, sorry. We're calculating the flow rate here. Sorry, let me write a Q here. It's the same in both places, but we want to calculate it in the place where we know the radius. Okay, we don't really know the radius of the bag. Okay, so V2 times pi times 0.0003 meters squared. All right? So we say that equals 3.5 times 10 to the minus 8. The whole point of this whole thing is just to get the velocity. Okay, the velocity of the solution depends on the flow rate you're trying to put in. So the velocity and the flow rate are always tied together. So if we solve that, we get that the velocity, 2, is 0.124 meters per second. Okay? So at a microscopic level, that's pretty fast, right? This liquid is 10 centimeters a second is shooting into your vein. It's going to slow down pretty quick because it's going to bump into stuff, right? But so now you have that V2, okay? And then you got to decide which one of these are we going to apply, these formulas here. Are we going to apply, which approximations can we make? Well, clearly, the opening of the catheter is very small compared to the bag. I didn't even give you the size of the bag. But you can see in the picture, right? The bag is like this big. The catheter is very teeny. So we could definitely apply that approximation where we don't worry about this. We don't worry about the bottom part. We just write this. Okay? So we're going to do the sort of small leak approximation. Where did the A go? Here it is, pi r squared. There's the A. Okay, so we're going to... we're having so much fun. We'll just keep going. We will do the break. So we have a small catheter. Actually, I'm going to build up tension, and we're going to stop because I'm going to lose my voice. All right, so 5 minutes, and then we'll figure out if you get fired from your candy striper job or not. 204. All right, I know some of you can't wait to hear the answer, so we better keep going. I got one exam question. Somebody asked, is torque going to be on the exam? Well, that depends on how you handle the exam. If you pick it up like this, then there's no torque on it. But if you walk up and pick it up like this, then it does have torque. So I guess that's what you meant. Okay, so it's a slow crowd. Let's see. It's a tough room. Okay, so where were we? We're saying, the catheter's small. So, so we get rid of the denominator, and we have that expression. So now are we smart enough to plug in the right numbers for that expression? Maybe. I'd give us about a 50-50. And we say V2, which isn't really what we're solving for, but we know V2. We'll plug it in a minute. It equals that, the square root. We might as well just put in the numbers, right? So we know V2 was 0.124 meters per second. Is a square root of the difference in the pressure, right? What is the difference in the pressure? Well, the bag is at what? Oh, we got to think about the bag for a minute. What is actually happening with the bag? If you zoom in on a bag, it's like it's closed. They're sealed, and there's no air in them, mostly. So the bag is soft is the point. So in this thing, the pressure was changing because it's a rigid container and air gets sucked out of it, right? And since it's rigid, the air lowers its pressure above it. But if it's soft, if it's a bag, then that doesn't happen. So basically the bag stays at atmospheric pressure because it has soft sides, okay? So then we would know that it's P2 times P atmospheric minus, and then the P at point 2 is here. So is your blood at only 50 millimeters of mercury? Maybe on Mars, right? But here we also have atmospheric pressure pushing on it. Okay, so we want the absolute pressure here, not the gauge pressure. So we would say the pressure there is really this plus P atmosphere. Okay, again, if you ask the doctor, what's the pressure in a vein, and he says 50 millimeters of mercury, and you say, don't you have to add atmosphere to that? He's going to say, what? Okay, but you have to know, because you're a physicist, that, yeah, in this equation we have to add 50 mmHg minus P atmosphere. See, the point is it's just the difference, right? The two P atmospheres are going to cancel. Okay? The point is that the liquid has to go into an increase of pressure of 50 millimeters of mercury, which actually is negative in this expression because of the way we set it up. It's okay, though. Don't worry. So that whole thing divided by the density of the solution, 1020. So we got 50 in the wrong unit over 1020. That's the first part. That's 2p minus p2, or whatever it was, over rho. And then plus, in this part, is 2gh, right? So times 2 times g is 19.6. I'll just be confusing and do that. There's 2g. And there's h. What is h? Oh, we're looking for h. That was the whole, that's what you were told to do. Calculate how high you need to put the bag. Right? And then I squared both sides and here. So pretend this is a new board here, because it doesn't matter here. So you all go down. I'm going to write here. I squared both sides. I got point, if you want to check your numbers later, 0.0154 is the square root of minus 13 plus 12.6h. If you tell me something's wrong with that, I'm just going to tell you that you probably made a mistake. Okay? So to get to that point, I converted this to pascals, to newtons per meter squared. The quick way is to say, well, that's 50. I know an atmosphere is 760. So you say 50 over 760 times 101.325. Or you just ask Google, convert 50 millimeters of mercury to Pascal. Either one, but not during the exam. I thought it was supposed to be P minus P atmosphere. No, it was, well, okay, because in that problem, the difference of the two, it's really just the difference of the two pressures. And it depends on what they are. So in this case, we're saying P1 is P atmosphere, P2 is P atmosphere plus 50 millimeters mercury. So if you screw that up and this comes out positive, then the answer's wrong. Okay? Let's see, is there still, okay, let's just finish it real quick. What do you get? You get H equals 0.66 meters. Is the answer to our question. Okay. Let me answer these real fast. Where did the 0.0154 come from? That's when I squared both sides. I squared 0.124 to get that. Why is there still a square root on the right? Oh, well, there shouldn't be right now. Okay, there we go. There, you're right now. There we go. Right. Anyway, you solve for H. And you get, that doesn't look right, does it? 12 over 16. I can't read my handwriting here. You get 0.66 meters. 0.3 over, yeah, I don't know. Finish it yourself, okay? You get a number. You get a number of meters. And yeah, I think I just have an algebraic error. 13 over, yeah, I probably had a typo. Anyway, you get a number. Is the number correct? Is your patient going to live? No, your patient's going to die. Okay, the number's too small. You get a number, I got 0.66 meters. You can see it's actually closer to a meter because 13 over 12.6, it's around a meter. Are these things really at a meter? Maybe. They're a little higher than that. It's roughly a meter. But the thing we didn't include, see that's, okay, well it's about a meter. Well, crap, okay. We didn't include viscosity. Okay, usually when you do this calculation, you have to add viscosity because there's a resistance to flow. So you need extra pressure. So the answer we got is actually a little small. It actually has to be bigger because viscosity also slows things down. We're not doing viscosity, but I'm just letting you know that if you have to make this calculation in a hospital, you know, don't forget about viscosity. Go take a better class where you learn about viscosity. Okay? That's it for fluids. Okay, we're done with fluids. Oh my God. Yay! Now we get to do oscillations. Whoa. Let's see. So now we go into the next topic, which is actually good review for the exam. So, you know, there's that. Yay! Although we won't get to the good review part. Oh. Okay. This needs to go away. All right. I'll just start here. Okay, with this next topic, we're inching our way towards like waves and light and all that sort of more fun stuff. Okay? So this next section is, the chapter is called Oscillations. Okay, we're just going to do fun stuff now because there's only 15 minutes. We're going to do it fun. So oscillations, you know what that is. Repetitive, back and forth motion. It could be a lot of things can oscillate. Anything vibrating is oscillating. Anything moving in a circle is technically oscillating. A mass on a spring is oscillating. Right? So this is our baby's first simple harmonic motion is always, oscillator is always mass on a spring. Yes. If you decide to be a physics major, I'm going to get one of you. You're going to spend like a year on that. Oh, wow. Okay, not a year. You'll use two of them, and then it'll be a year. So let's start. Our first oscillator is start with simple harmonic motion, which is usually abbreviated I like to abbreviate SHN. And it's not M. It's not simple. Okay? Nothing is simple. But simple just means it's moving at one frequency, basically. Harmonic means frequency, simple means one of them, and motion means it's moving. So we actually did this already. We were talking a little bit about describing motion at fundamental level. We sort of already did this. We said, if you have a mass M on a spring K and its natural length is that the origin O, how's it going to move? And we said, okay, well, how anything moves, it's Newton's second law. So you say sum of the forces minus Kx, if we're just doing the x direction, equals ma, but just to move quick, we'll say ma is a second derivative of position with respect to time. Oh, yeah. Right. And remember, I was like, what function can you think of that's equal to its own second derivative? And the answer was that you guess. Remember that whole fun thing we did? Nobody came down, one person. Yeah. So that's all this you guess. Differential equations, that's what's happening in that class, 103 or 4, whatever it's called here. Okay? You guess, but now we're going to get a little more sophisticated. So last time we guessed, but, we just said sine. Okay, let's guess with a little bit more purposefulness. All right. We're going to guess. We're going to guess sine. I heard somebody whisper it. I don't want to disappoint you, so yes. We're going to guess. We're going to construct our solution, as the mathematicians say. So yeah, sine. Okay, here. Are we done? No. Let's draw a sine. Let's see. And let's think, does the thing really move like a sine? Yeah. You can see it moving up and down here. It's kind of like a sine, if you know what a sine looks like. If you can imagine a sine. The sine of 0 is 0. So we could draw a sine real quick. Like that. So that is sine, but this is like the math world. We need the real world, right? So we want to guess, did that fall off? Did everybody have their protective eyewear on? No, okay. So solution needs parameters to make it like a physical expression, right? Things have units. We can't just write sine. Okay, so let's think one parameter is as this thing was moving up and down. The highest it goes is we call the amplitude of the sine wave, and the lowest we go is minus a. Right? So if you have a sine wave, you know that it goes from some value maximum to some value minimum. And you know in a sine for math where that goes. It goes right there. Right? Because sine goes from 1 to 0, so if you multiply by a, it goes from positive a to minus a. Right? So when we make our guess, we would probably put an A there. Right? And then you'd say, okay, sine, and just put a T here. It's like, no, you can't just put a T there. Let's go ahead and put the T there. Right? It's a function of time, but you can't actually take a sine of something with a physical unit. Okay? You can't take a sine of something with time. You can't take an exponent of something with time. You can't take a cosine of something with time. The only unit you're allowed to have in here is radians. Right? So you've got to have radians in there. So we have to convert that sine, or that t to radians, so we should look back at our sine wave and think, is there some parameter that would allow us to do that? And that parameter is the period. It's how fast the sine wave happens. Right? So t is what you've heard of before, is the period. When we were talking about circular motion, these are all the same ideas. 1 period equals what in radians? 2 pi radians. Right? 1 period is 2 pi radians. So if we want to convert, what this thing really wants to know is how many radians has it gone through? Well, at a certain amount of time t, it's gone through 2 pi over t radians. Right? The time, the variable time over the period is how many cycles it's gone through, and one cycle is 2 pi. Okay? When you're doing circles, one circle is 2 pi. When you're doing cycles, one cycle is 2 pi. A cycle and a circle are the same thing. And depending on your accent, they are actually the same thing. And then we've got another thing here. So let's see. So inside the sine must be radians is sort of our justification for this. But then we need one more thing. Oh, this is the bad one. Oh, no. Is we have to have a phase plus phi naught. Right? It's just a phase. Don't freak out, okay? It's just phi naught. Everybody freaks out about what the phase means, okay? And here's the reason we have to have a phase is, let me set it back up. Somebody knocked it off. Right? When we set it back up, sine is at 0 at time equals 0, right? And we put it over here. So sine is at 0 at time equals 0, but does it have to be at 0 at time equals 0? Right? Time equals 0 could be now, or now. Or if you're really smart and know how a sine works, now, right? So it doesn't have to be 0 at 0. Right? I didn't even label this as 0. You just thought it was 0. Actually, I meant to say, oh, down here is 0. Oh, right? So here's time equals 0. Okay? So all phase does is it shifts the curve left and right. Shifts the, I'll call it the curve, you know what I mean. Left and right, assuming you have time, on the x-axis. So it's just a little constant to help you decide where 0 is. Okay? If you're smart when you set up a problem, you pick sine or cosine correctly so you don't have to deal with a phase. But you're learning that. Okay? So this is the guess we would make right here. A sine 2 pi over period t plus phi naught. And then that has like all the free parameters you need. Okay? Oh, now I have too much time. Okay. So now we're going to keep going. We're going to bring this down. We're going to turn this on. Right? Okay. Because I want to stress the difference or the similarity of these two. All right. Okay. So we have this. And okay, we've made a guess. I think it was a good guess. A sine 2 pi over t plus omega naught. So now we're going to plug it in to check it. It's possible we've made a bad guess. Highly unlikely I would do that in my notes, but I might have screwed it up. You never know. So this is how differential equations works. You guess, you plug it in, and when you plug it in, you learn what the parameters are. Ah, okay. But first, and I know you're excited to do that, but first, switch to omega is 2 pi over t. So you may recall circular motion, right? So something is going around in a circle. This is going around in a circle. No, there will not be torques on the exam. Omega. Omega here, well, what is the same thing as 2 pi over t, the angular velocity. It goes around a full circle in the period of 2 pi. So what we can see is that really omega and t are circular motion and harmonic motion are the same thing. Okay, so here you can see the shadow of the little thingy moving up and down. Oh, and over here you can see the shadow of this moving up and down. And they're both in harmonic motion. See how they're both in harmonic motion? If I really cared, I would make them at the same speed, but there's a limit to how much I care. Right? But you can see, you get the feel for what harmonic motion looks like. And look at this harmonic motion up and down like that. Same thing. Okay? So the omega means exactly the same thing. You go through a cycle, which is 2 pi. You can either call that a circle or just a cycle of a period over t. And it's the exact same thing here. Okay, that's not harmonic motion. Oh my God. That's not quite harmonic because it has mass and stuff. This will be harmonic for a long time. I'm just going to leave that there to hypnotize you. Okay, so we're going to switch to omega in our guess, right? Okay, so let's plug it in and see what happens. Plug it into what? I forgot. What do we plug it into? We guessed from the equation of motion. We guessed from Newton's second law. So let's plug it into Newton's second law. Okay, minus k times what? Times x. So let's write it. Minus k times a sine omega t. See, omega t instead of 2 pi over tt. That's nicer. Plus the phase. We don't know what the phase is going to be. Equals, let's see, it was minus kx. equals m, and then it was d2x dt2. Sounds like a Star Wars robot, but it's not. It's the second derivative. And you say, I got to take two derivatives real fast in my head because I've had a lot of calculus. You say sine, you take the derivative of sine, it goes to cosine, and you have to multiply by the derivative of the argument with respect to time. So it turns out it's just omega. Derivative of omega t is just omega. Derivative of phi naught, a constant, is 0. So it just pulls out an omega. A omega cosine omega t. But then you do it again, and cosine becomes negative sine, and you pull out another omega. And you go back to sine. Okay, that was the calculus part. Sorry about the sleight of hand aspect of that. Okay, so it says that if you guess that this must be true, right? That's the guess. We guessed, we plugged it in. Newton says this. Newton 2 says, that's a great guess. If this is true, like you talk to the equations, right? You guess, you say, hey, Newton's law, is this right? And Newton says, yes, that is correct if this is true, right? So is this true or not? A's cancel. The pluses, the minuses become a plus. The sine omega t plus phi naught cancels. So it's true. Newton, the ghost of Newton, says it's true if k equals m omega squared. All right? The ghost of Newton told me that. And then you say, okay, well, that doesn't mean anything. But it does, because one of those is part of the guess, and two of them are part of the system. Okay? Two of these are given to you in the problem, the spring constant and the mass. These are given. These are physical things. And this is part of the guess. So basically, when we made the guess, Newton told us what the frequency is. Omega is the square root of k over m. Newton is literally talking to you and saying, that's a good guess. It will move like that if it goes at the square root of k over m. Okay? Can this thing move at any frequency other than the square root of k over m? No. Okay? So I can give it a big amplitude. If you were to time it and get its frequency, it would be omega would be the square root of k over m. I can give it a small amplitude. And you can probably kind of tell if you just kind of snap with it. Hey, everybody. No, I hate that. Let's not do that. You can kind of tell it's basically the same period. It's the same omega. No, please stop. And it goes like that. See? Same frequency, or the same angular frequency. So omega is a property of the system. You can't change it. Okay? Now I better go back to my notes, or I'm just going to completely go crazy here. Okay. So omega is a property of the system. So now I know you're stressed. I know you're worried about A and phi. What do we know about A and phi? Let's see. Omega is a property of the system. Oh, wonderful. I know you're worried about A and phi. Is m the mass of the spring or the block? Oh, it's the block. We wrote Newton's second law for the block. The spring is massless. It's just applying the force. Yeah, let's see. So we concluded that omega depends on the system. That's what Newton's second law told us. Newton's second law also told us something about A and phi. A, phi. Who cares? Okay, Newton says A and phi can be whatever you want. I don't care what A and phi are. My law doesn't determine A and phi. Is that true? Yes, because look, A can be big, right? Or A can be small. It can be big or small. What about phi, the phase? That could be anything, because I can say t equals 0 at any time I want. T equals 0 now, right? Or t equals 0 now. It actually doesn't, I don't have to watch it at a certain time, right? T can be equal 0 anytime. Okay, so A and phi are free, and omega was defined. Okay? So now what we want to do is see, let's see, this would be a better use of our time. Yeah, we're going to skip phase for now because I want to get to the part that might help you think about the exam. Let's do that. We'll get back to phase when we get back. Okay, because here's what I want you to know for these problems, but also for the exam it might help. So once you have x of t, you have everything. Okay? Right, so if I now can write down an equation for this motion, I can do it all. All right, so let's write it down. Let's say our guess was correct. A sine, we could even get technical and put k over m here, t plus phi naught. Okay, I'll tell you how to get a and phi naught next time, but for now, just don't worry about them. Well, I could also write down the velocity. This is the position at a function of time for all times. I could also write down the velocity for all times just by taking a derivative. Oh, let's go back to calling it omega. But, well, okay, it's fine. Derivative of sine is cosine, and we take the derivative of this with respect to time and pull it out, right? So it's a square root of k over m cosine square root of k over m t plus phi naught. So now I know v. Let's see. So what else would I want to do? I could know the acceleration at all times. Okay, the derivative of cosine is negative sign, negative. We pull this out twice. It becomes k over m because we pulled it out twice, right? The square root of k over m squared is k over m. And then it turns us back to sine. So with those three, I could write down any expression you want. Right? What if I want the momentum? What if I want the momentum as a function of time? How would I get it? I would say, oh, the momentum is a function of time. T, it's mv, right? I say a m square root of k over m cosine square root of k over m t plus phi naught. And I could start combining things and realize that's actually square root of km if I wanted to. You don't have to write this part down. I'm just giving you an idea, right? So now I know the momentum is a function of time. Okay? But now let's think in terms of this exam. You might think, now wait a minute. Is this momentum constant? No. Right? Here we have a case where momentum is changing, and momentum is supposed to be conserved. So what's going on here? Well, the spring is applying an external force. It's doing external work, or in the case of momentum, it's applying an impulse to the mass. Right? So it's okay that the momentum changes. But what if we tried to isolate the system? So let's say like this. So this is not on the exam, and this would be a little bit weird, but here's an example problem. So say the spring's natural length is here, right? And this is the mass m, and this thing is floating in free space, right? It's magically held outside of its equilibrium position, and it's released. What's going to happen? Right? So on the final exam, we could ask, how will the mass move? And you'd say, oh, it undergoes simple harmonic motion. And then we would say, does this thing move? Right? Does that thing move? And you'd have to say, actually, that has to move. Because this is an isolated system. It's sitting there with its momentum is 0. Right? Momentum is 0. Suddenly, some little lever, internal mechanism, releases the mass. And if this thing starts moving this way, to keep the momentum 0, this whole thing would have to move that way. Right? They would have to move together, and they would move in a way where the center of mass would stay still. Okay? Not on the exam because it's about springs and oscillating motion, but you see the idea. Okay? Then you might say, well, if you set this something on the table on a frictionless surface, wouldn't the thing still have to move? And the answer is yeah. You would actually be pushing the Earth. The Earth and the mass would be kind of going, but the Earth is so heavy you wouldn't notice. Okay? But if their masses were kind of similar, you could kind of see these two things vibrating together. Okay? So you got to think about conservation of momentum, whether something is isolated or not. If it's not isolated, you could think of it as, if this is the isolated system, then the spring is applying an impulse to the mass. If this is the isolated system, you acknowledge, actually, this will move. You could go either way. All right. We could even do, real quick, oh, this is the exciting part. From here, we could do the energy real fast. Let's write the energy. We'll do it again Tuesday, but let's just write it because it's very exciting. This will light it up even better. You'll be able to see it. Could you calculate the energy from all this? I bet you could. What is the kinetic energy? As a function of time, 1/2 m, and that v squared, right? 1/2, what is m? M is the mass. What is v squared? A squared. What is square root of k over m squared? K over m. What is cosine squared? Cosine squared. Right? There's the kinetic energy as a function of time. Anything interesting happening there? Look at that. The maximum of the kinetic energy is 1/2 ka squared. That's weird. What if we said, what's the spring kinetic, the spring potential energy. It's 1/2 kx squared. 1/2 k x squared is a squared sine squared square root of k over mt plus phi naught. Huh, that's weird. They both have the same amplitude in front of them, 1/2 ka squared. They have the same energy. If you were to plot these, you have to know what squared sinusoids look like, but it's not hard to figure out. They stay positive, and they still act like a sinusoid. Right. So at time equals 0, we'll assume the phase is 0. Cosine is 1, so this would be what the k would look like. It doesn't go negative, it stays positive. Right? This is k. That's the kinetic energy through one cycle. This is where the position would have gone negative, but it doesn't because we squared it. Or this is where the velocity would have gone negative. Right? And then, I don't want to go too far over, but this is interesting. Oh, I got 2 minutes. Now I want to plot the potential energy. It's a sine. A sine at 0 is 0. We'll ignore the phase. There's no phase. I don't know what you're talking about. And it goes sinusoidal with the same amplitude, 1/2 ka squared. Right? Starts here, and it goes like this if you were to plot it out. Like that. That's hard. They're right on top of each other. I know it's hard to see. Right? But what if you added them together? What would you get? The energy is constant. Right? Using these little expressions from simple harmonic motion, we can see that the energy, the mechanical energy of the thing, doesn't change. It's constant. Okay? What if you had to do it mathematically, not graphically? Oh my God. What if you added these two things and pulled out a 1/2 ka squared? What would you get? Sine squared plus cosine squared. What's sine squared plus cosine squared? 1. Where'd the time dependence go? It's gone. Right? The energy is constant with time, mathematically as well. So this all matches all the stuff you're doing on the exam. All right.